Hello there, kids. This is your ma'am Akshita, and I welcome you all to the most amazing learning platform. And now we are going to summarize whatever we have learned in our very first chapter. And what have we learned in our very first chapter? Let's start with the name of the chapter, which is Chemical Reactions and Equations. That is our very first chapter. And in our session today, we shall be summarizing everything that we have learnt during our sessions. So what all have we learnt in our sessions? We have learnt about the various properties of a chemical reaction. Then we learnt about the chemical equation, then types of chemical reactions and effect of oxidation in everyday life. So we are aware and we have come across all of this while we were learning it. Today, however, we shall summarize this. So let's start with our session with the very first thing, which is chemical reactions. What are chemical reactions? What comes to your mind when you think of chemical reactions? Everything around us is the product of some or the other chemical reaction taking place. The food that you eat, okay, the curdling of milk, the nice curd which you like having, all of these are nothing but the products of chemical reactions taking place in our everyday life. You know, the reactions like the grapes getting fermented, okay, the iron tawa, pan or nail which upon exposure to humidity, the change in its color which we call rusting, about which we shall be learning now. And then food which gets digested in our body, the respiration process which takes place. All of these are nothing but examples of various chemical reactions that we come across in our day-to-day life. So whenever a chemical change occurs, we can say that a chemical reaction has taken place. Whenever there is a chemical change that is happening, it is occurring, we can say that all right, since a chemical change has happened, then definitely a chemical reaction is taking place. But what are the changes? The changes are either in the form of the state. The state might change. We know states are of three types. We know that this particular state is of three types. One second, the state is of three types. It can be solid, liquid and gaseous state. So when there is a change in state, we can say that all right, a chemical reaction is taking place. Then if there is a change in color, even then we can say that okay, fine, there is a chemical reaction taking place. Then when evolution of gas comes into picture, that is when gas is released, even then we can say that okay, a chemical reaction is taking place. And finally, when there is a change in temperature, we can say that all right, a chemical reaction is taking place. Now, it is not necessary that all the four properties, that is all the four changes or all the four that you can see on the screen are going to take place at the same time for a given reaction. Not necessary. Either one of these criteria or two of these criteria can also justify, they can also be present, and then we can say, all right, fine, a chemical reaction is taking place. So it is not necessary that all the four shall and must, should and must take place. No, not required, but at least one of them should definitely take place for us to say that all right, a chemical reaction is indeed taking place. Let's now look at the example of change in state. Now, what happens when there is a change in state? That is, the state is undergoing a change. That is, either it is turning from solid to liquid or liquid to gaseous state, or directly from solid to gaseous state. Any change in the state must take place. All right, any change in the state must take place. The example that we can see is combustion of candle wax. We are already aware of the candle wax. Okay, when this candle wax burns, okay, when its combustion takes place, then what do we see? There's a change in state from solid to liquid. There's a change from solid to liquid. Another example that you are aware of is when ammonia gas reacts with hydrogen chloride, we get a salt which is ammonium chloride, which is solid in state. So here you can see that the gases are interacting and the product that we get is solid. That is, change of state is actually taking place, right? Then talking about change in color, we have n number of examples for change in color. The most common example you must come across is copper sulfate. When this copper sulfate is treated with iron, I'm sure you must have done this, in the laboratories, the reaction undergoes a displacement reaction. This particular solution undergoes a displacement reaction, wherein the blue color copper sulfate, we know copper sulfate is a beautiful blue color, but when it comes in interaction with iron, what we get is a green colored solution, and this green colored solution is the result of the formation of ferrous sulfate. Okay, it is because of the formation of ferrous sulfate, and upon the iron you will see the deposition of red colored powder, which is nothing but copper which is being deposited on it. All right, so is there not a change of color? That definitely is a change of color. Then evolution of gas is the third thing that we are aware of. We are, aware of this thing since we have been learning it in our 8th grade as well. That when a metal reacts with an acid, what happens? Hydrogen gas is liberated. And we have learnt about this in detail, and we will learn about this in detail in acid, bases and salts, which is the 2nd chapter. But you're already aware from your prerequisite knowledge that when a metal is reacting with an acid, what we see is this hydrogen gas is released. All right. So evolution of gas is also what we have seen and we have come across. Then change in temperature. That is when there is a change in temperature. Let's say when you have started the reaction, the temperature is T1. Okay, and after some time the temperature is T2. Now this T2 can either be greater than T1 or it can be lesser than T1. There are two possibilities for it. All right, what are they? How are they? We will learn about it. Don't worry. But we are already aware. We know that, okay, when we start the reaction, the temperature is T1, and after some time, the temperature is T2. That is, there is a change. There is a change. And this is seen when calcium oxide reacts with water. What we get is calcium hydroxide, which is nothing but slaked lime, and a lot of heat is released. You can see that when you touch the beaker, after the reaction is done, after the calcium hydroxide is formed, you see that it's warm. Okay, it's warm. Why? Because heat is released. Such reactions are exothermic reactions. We will again summarize, we will again learn about it, but just briefing you up over here. So with this, we have understood the various properties of chemical reaction and how you can characterize a chemical reaction based on these properties. Then, how do we write a reaction? See, multiple reactions take place around us. Multiple reactions. And you must have seen I have written them down. Why? Because when it comes down to learning, you write them down, don't you? But how do you write it down? There are various ways in which you can write it down. You can write it in the form of a sentence that calcium oxide reacts with water to give rise to calcium hydroxide with the liberation of heat. That is in the form of a sentence. You can also write it in the form of words, okay, with symbols involved. And such equations are known as word equations. Okay, the most famous example which people take and which you have performed in the laboratories is the burning of magnesium in the presence of air to give rise to magnesium oxide. Why is it so famous? Because of the dazzling flame that you see, is it not? So, how do we write it? See, we can write an entire sentence that magnesium reacts with oxygen present in the air and it releases a dazzling flame with the formation of magnesium oxide. You can write an entire sentence. But is it possible for us to write sentences for all the reactions that we come across? That takes up a lot of time. So the best way to tackle this is with the help of word equation, where we can say magnesium plus oxygen, because magnesium is reacting with oxygen, gives rise to magnesium oxide. Okay, here magnesium plus oxygen is the reactants. Okay, the ones that you see on the left hand side are your reactants, and the one that you see on the right hand side are your products. Okay, and these reactants give rise to products are shown with the help of an arrow. It is shown with the help of an arrow where the tail of the arrow faces towards the reactants, whereas the head of the arrow faces towards the products. Okay, so this is what and this is how a word reaction or a word equation is written. All right. And you can also say that the reactants are present, since they are present on the left hand side, we can say they are present on the left hand side in the form of LHS. And products, since they are written on the right hand side, we can say they are present on the RHS. The short form, the acronym of right hand side, RHS, for left hand side, LHS. So with this we have seen how a chemical equation, or I would rather say how a chemical reaction is depicted in the form of a word equation. And the arrow, the way in which the direction in which the arrow points or faces is showing in which direction the reaction is actually taking place. All right. So this is about the word equation. But now tell me, can you always write the word equations like magnesium plus oxygen gives rise to magnesium oxide plus, light? Huge equation, is it not? So the best way to put it forth is with the help of formula. We know elements, compounds have a certain formula. All right. So with the help of these formula, we can depict the entire chemical reaction in the form of a chemical equation. And how do we do that? Let's say A is interacting with B to give rise to C plus D. Here A and B are reactants, C plus D are products. Okay. The arrow points towards, or the direction of the arrow tells the direction in which the reaction is taking place. Okay. But what if I give elements over here? What if I put in compounds over here and show their reaction? So instead of writing those compounds or elements in the form of their words, we can write them in the form of their formula. And upon doing that, what we arrive at is a chemical equation. For example, hydrogen plus oxygen gives rise to water. This is a word equation, is it not? But I can use the respective formula H2 plus O2 gives rise to H2O. This is nothing but a chemical equation. Alright, so we can show chemical reactions that are taking place in two forms. One in the form of a word equation, another in the form of a chemical equation. The only difference being between these two is that the elements and the compounds which are reacting and the products which are forming are written in their respective formula in chemical equations. Whereas in word equations, what we do is we write their names. All right. So that's about chemical equations. But you can see this H2 plus O2 plus H2O. Okay, this H2, one second kids. The color is important. This H2 plus O2 giving rise to H2O. Now when you see this H2 plus O2 giving rise to H2O, what do you observe over here? Are the number of atoms of hydrogen in the reactant side same as that in the product side? Or are the number of the atoms present of oxygen same as that on the product side? You will notice that the number of atoms of oxygen in the reactant side and the number of atoms of oxygen in the product side are not same. They are not same. So what do we do about it? And what are such equations called? So this right now is an unbalanced equation. It is an unbalanced equation. There is no balance between the reactant and the product side with respect to the number of atoms that are there. All right. That is, the number of atoms reacting in the product side of a given element should be equal to the number of atoms formed on the product side of a given element. But that is not what is happening over here. So this is known as an unbalanced equation because there is a misbalance. There is no balance between the reactants and the products with respect to the number of elements that are there on either side. So what do? We balance these equations. We balance these equations. But what is the need to balance these equations? You are already aware of law of conservation of mass. Law of conservation of mass, which you learnt in your 9th grade under the chapter Atoms and Molecules. What does this law state? In simpler terms, if I have to say, it basically means, or it basically states that mass can neither be created nor destroyed. You cannot create or destroy mass. That means, according to the law of conservation of mass, the mass of the products in the chemical reaction must be equal to the mass of the reactants. Now that is possible when the elements, the number of elements present in the reactant side are same as that present in the product side. So let's say if 2 moles of hydrogen are reacting, that makes 4 atoms of hydrogen. That means in the product side we should have 4 atoms of hydrogen. Let's say if 2 moles of oxygen are interacting, that means there are 4 atoms of oxygen, right, which are interacting. Then in the product side also we should have 4 atoms. We should have 4 atoms of hydrogen. So what do you observe? What do you understand over here? That the number of elements, the number of atoms of elements present on the reactant side must be equal to that on the product side. How do we achieve it? Now that again is a task. Okay, but a very easy task if understood properly. What we practice over here is hit and trial method. Alright, and there are certain steps that we follow. Alright, when you put forth these steps, okay, eventually you will get the hang of it. It's then gonna get easy for you. But till then you have to follow all these steps in the given fashion. Once, twice, thrice, 4 times when you practice it, you'll get the hang of it. Alright, so shall we begin? So let's now understand how to balance a chemical equation. So here we have a chemical equation, or I would rather say a word equation, wherein zinc is reacting with sulfuric acid to give rise to zinc sulfate and hydrogen. Is it not? So we know that this metal is interacting with an acid to give rise to salt and hydrogen gas. Now how do we write it in the form of a chemical equation? We put forth their formulae. That's exactly what we did. Zinc is represented as Zn, sulfuric acid as H2SO4, zinc sulfate as ZnSO4 plus hydrogen gas. That is what we see over here. Now we have to check whether the elements, okay, their atoms as given in the reactant side must be same as that in the product side. So what do we do this? We draw a table. As you can clearly see, a table is drawn wherein the first column is dedicated to elements. The second column is dedicated to the number of atoms in the reactant side. That is nothing but your LHS. Alright. And then we put in the number of atoms in the product side, which is nothing but your RHS. So let's see for zinc. We have one atom, or I would rather say 1 atom of zinc reacting. Okay. In LHS, 1. Let's now look at the product side. Only 1. So we write 1 over there. Then we look at hydrogen. There are 2 atoms of hydrogen. There are 2 atoms of hydrogen in the reactant side. We write 2. In the product side, when we check, again 2. Alright, 2. Then we'll check for sulfur. 1 atom of sulfur. Okay. In the reactant side also 1. 4 atoms of oxygen. In the reactant side also 4. So 4 and 4. What do we see? That LHS is equal to RHS. Is it not? LHS is equal to RHS. What do we understand by this? That LHS is equal to RHS. That means the atoms, the number of atoms of the given elements in the reactant side is same as that of the given elements in the product side. That is, the number of elements on the reactant side and the product side are balanced. So this thereby becomes a balanced equation. Now you must be wondering, ma'am, you said we will learn how to balance. And now you're saying this is a balanced equation. Where have we learnt about it? Now don't you worry. This is for you to understand how to check whether it is balanced or not. Now we will learn how to actually balance an unbalanced equation. Okay? So as the number of atoms of each element is same in both the cases, so that was a balanced chemical equation. This we have understood. Let's now try to balance this equation. Iron reacting with water to give rise to iron oxide, which is nothing but ferric oxide plus hydrogen gas. Okay, we have to now balance it. So there are a certain few steps that we have to follow. Let's begin with step 1. To balance a chemical equation, first draw boxes around each formula. Do not change anything inside this box while balancing the equation. Let's say I'm trying to balance iron. Let's say I draw a box around iron. Okay? And I draw a box around iron over here. And then I will check for the atoms. This is for you. This is for you to put forth your focus on one element at a time. Alright? You don't really have to do this, but if at all you're finding difficulty, then you can start off with this method. Alright? Then after that, what we do is, we list the number of atoms of different elements present in the unbalanced equation. So the same thing that we did previously, we will now again draw a box and we will divide it into respective columns, where one, we write about the element, then the LHS, which is the reactants, and then the products, which is the RHS. So starting with iron, we have 1 atom of iron. Okay, 1. In the product side, 3. Oh, there is not a balance over here. Okay. Let's now check with hydrogen. 2 atoms. Okay, 2. Product side also 2. Okay, so hydrogen so far is balanced. Will it be balanced till the end? We shall check. Oxygen 1. Here it is 4. So you can see that iron and oxygen are not balanced. So we will try balancing them. Okay. So in step 3, it is often convenient to start balancing with the compound that contains the maximum number of atoms. In our case, it was oxygen, that is the oxygen present in water, and Fe3O4. Okay, oxygen. So we will first balance oxygen. Why? We can start with iron also. But why do we start with oxygen? Because it is convenient to start with the atom, the element. Okay, the atom which has the greater, the element which has greater number of atoms. Okay. So it may be either on the reactant side or the product side, obviously. So here it is oxygen. Oxygen that is present in the reactant in the form of water, and in the case of products, in the Fe3O4. Okay. So H2O has how many? We again draw the box and we write initial atoms of oxygen first. Then in reactants in the product side. Then in the atoms of oxygen, we'll first write initial. Then what do we need to do to balance it? So in initial, we have only 1. H2O. Only 1 atom. Okay. In the case of products, we have 4. 4 in Fe3O4. Okay. There is a mismatch. Here 1 in the reactant side, in the product side 4. Now we have to balance it. How do we balance it? By making it equal. How do we make it equal? By multiplication. By multiplication. So now we have 1 atom of oxygen and we have 4 atoms of oxygen. This is in reactant, this is in products. Now I have to make it equal. This is, let me write oxygen because you might think it's 10 and this is 40. Okay. Now how do I make it equal? By multiplication. So it is easier for me to make 1 equal to 4, right? By simple multiplication. So 1 into 4 is what I do. Alright. 1 into 4 is what I do. And as a result, I get Fe plus 4H2O plus Fe3O4 plus H2. Now another thing. This 4 is written as 4H2O. Alright. That is 4H2O. To this we are adding 4. You are not supposed to disturb anything inside the box while it is being balanced. You don't write it as H2O4 or H2O taken 4 times. Okay, because O4 does not exist with H2 like this. It's wrong. Okay, because when you write H2O4, 2 ones are 2 twos are, it becomes HO2. Is this what we are trying to achieve? No, right? And when you write H2O4, that means this 4 is multiplied to hydrogen also. So that becomes 2 into 4, 2 into 4, that is 8 molecules of hydrogen and 4 molecules. This is not right. Thereby, you attach it as a coefficient. You attach it as a coefficient in front of the compound which you are trying to balance. It becomes 4H2O. I hope we are clear till here. Okay. Now what are we left with? Fine, we have balanced the oxygen, but now you see the hydrogen is not balanced. Here in the product side, we have 2 atoms of hydrogen, whereas in the reactant side, 4 into 2, we have 8 atoms of hydrogen. Now we see there's a mismatch. So let's balance. Now we can either balance iron first or we can balance hydrogen first. We can balance either of them first. But since, as I told, it's convenient to balance the compound or the element which has more number of atoms, in this case it is hydrogen. So let's balance hydrogen. Again, you draw a box. The first box, atoms of hydrogen in the reactant side, in the product side. Then initially how much do we have? 8. That is 4 into 2. That makes it 8 atoms. In the product side, we only have 2. Now, how do we make it equal? By multiplying. We know 2 into 4 is equal to 8. So, what we do is we multiply this with 4. As a result, we get Fe plus 4H2O gives rise to Fe3O4 plus 4H2. Now, hydrogen is balanced, oxygen is balanced. Iron is not balanced. We again draw the same table, that is atoms of iron, okay, in the reactant side and in the product side. Initially we know it is 1, Fe, and in the products we know it is 3, Fe3O4. So what do? We can make the reactant equal to products by multiplying the reactant with 3, and we get 3Fe plus 4H2O gives rise to Fe3O4 plus 4H2. This is what you see is our balanced equation. But this is not giving us the complete information. Why? Is this ion solid? Is this ion liquid in state, molten state? What is the state? You have no idea whether the state of the compound, you don't know whether this ion is in the solid state, this Fe3O4 is in the solid state or aqueous state. We don't know. So is it giving you the complete information? No. So what do we do? After checking that this entire equation is balanced, what we focus on is writing the symbols of the physical states. We write the symbols of the physical states, and the gaseous state, the liquid state and the solid state are given by the notation G, L and S, and the aqueous state is given as AQ. So we will then mention the physical states of them in brackets next to them, as you can see. Alright, and we also use arrows. Upward arrow means the gas is being released. Downward arrow means a precipitate is formed. So this is how we can make our equation more informative with respect to their symbols of their physical state. Also, there are certain conditions that are required, maybe for certain reactions a catalyst is needed. Now what is a catalyst, ma'am? Catalyst is that substance which does not participate in the given reaction. It increases the rate of the reaction or decreases the rate of the reaction. It is not participating in the reaction, but it is increasing the rate of the reaction or decreasing the rate of the reaction. It is enabling the reaction to either move in the forward direction, that is give rise to more products, or move in the backward direction. Alright, so we have a catalyst and we write this catalyst above the arrow. Sometimes certain pressure conditions, temperature conditions are also required. That also we write above the arrow over here. So as you can see, mentioning the states, mentioning the conditions, the criteria, okay, above the arrow completes the given equation. It gives a complete picture. How many atoms are interacting, okay, what state it has, is there a pressure requirement, temperature requirement, catalyst requirement. All of this is then given in a given equation, and this is a completely balanced equation which gives us all the information of the given reactions. So with this we have learned how to balance an equation. Now you must be wondering, okay ma'am, we have learned how to balance the equation. We have understood how to balance an equation. But we are getting these equations from chemical reactions. Are there any types of chemical reactions? Do they have types? If yes, then how are they different? If no, then how are they similar? What are the relationships between them? Are there any relationships between them? So many questions, so many questions. Let's answer them. Let's answer them. So chemical reactions, yes, are of 5 major types. They are of 5 major types, and they are different from each other, yet you can relate one or two with them. Okay, so what happens? What happens? Now we know that no atom undergoes any disappearance from the mixture, or they do not appear elsewhere. Okay, so chemical reactions involve the breaking and making of bonds. This is what you have to understand. See, we know that whatever is interacting, okay, is giving rise to a respective product. This we are aware of. But how is it happening? What is causing it? Well, let's say we have A and B. A, B is a compound. Okay. Now, only if it breaks, okay, and we have C, A reacts with C, we get AC and B. Now, what do you think is happening over here? Isn't the bond between A and B breaking to give rise to A and B separately? And isn't A reacting with C, interacting with C and forming a bond with C, and then giving rise to AC plus B? This is very similar to friendships, beta. Very similar to friendships. You can be very good friends with me, alright? But you might not be really good friends with somebody else. But then tomorrow, you might have an issue with me. You'll be like, no ma'am, you're being too strict ma'am, no ma'am. And then you go and make a bond, a friendship with someone else. There is a possibility. There is always a possibility. So what happens is, when there is a possibility of the formation or the breakage of bonds and relationships, these are nothing but just elements, compounds. And making and breaking of bonds, not baking, I'm so sorry. Making and breaking of bonds is what happens when a chemical reaction is taking place. And based on this making and breaking of bonds, chemical reactions are of 5 types. Addition reaction, decomposition reaction, displacement reaction, double displacement reaction, redox reactions. 5 of them. Weird names, confusing names. Don't you worry. It's easy and we shall understand it better now. So if I have to put forth, this is a simple mind map. Okay, this is a simple mind map which you will have a better understanding once we are done with the entire different types of chemical reactions. We will start with combination. Combination, as the name itself states, combining. The elements are combining. Decomposition. Decompose, to break down. The compound is going to break down and then we will get new products. Displacement. The place is going to be changed. Based on what? We shall see. Then double displacement. That is double displacement, double trouble. That means double means 2. So double movement. We shall see that too. And then redox reactions. Redox reaction is nothing but the combination of reduction and oxidation reaction. So we shall see all of them in detail. Starting with combination reaction. And I will start this with a small example. You take calcium oxide. okay, or quicklime in a beaker. And to this you add water, okay. What happens? So when you take calcium oxide, we have already seen this reaction in the case of change in temperature. What you do is, when you take calcium oxide, which is nothing but quicklime, and you add water to it, what you get is slaked lime. What you get is slaked lime, which is nothing but calcium hydroxide. And what do you understand over here? What do you understand over here? When you get calcium hydroxide, some amount of heat is also generated. But what does it give you? What idea does it give you? Let's say there is a compound A reacting with B to give rise to a single product. That is when two or more reactants combine to give a single product. It is known as combination reaction. Excuse me. It is known as combination reaction because combining, addition is taking place. They're adding on to each other. Thereby, combination reaction is also known as, addition reaction. Excuse me, kids. Okay. And calcium oxide is one compound reacting with water, and it gives rise to calcium hydroxide with the liberation of heat. Are we not getting a single compound? We are, right? We are getting a single compound. So what is it an example of? Combination reaction. Why? Because two reactants, that is nothing but calcium oxide, is interacting with hydrogen to give rise to calcium hydroxide, which is a single compound. Thereby, this is known as a combination reaction. Now you must be wondering, ma'am, heat is released. Does this have a name? Yes. Exothermic reactions. Exothermic reactions are chemical reactions where the reactants release heat energy into the surroundings. Okay? Heat is released into the surroundings. That is, when a reactant interacts and gives rise to products, along with the formation of product, certain energy is also released. And this energy is released into the surroundings. It is released into the surroundings, thereby giving a warming effect. That is why when you touch the beaker in which calcium oxide reacts with water, it is warm. It is warm. And this is because of the heat energy that is released. Thereby it is an exothermic reaction. So what are the other examples? Burning of natural gas is also exothermic reaction because heat energy is released. Respiration as well is a exothermic process. Respiration as well is a exothermic process, as you can see. All right, that is why they say when you eat food, digestion takes place. All right, and energy is released. Then how is this energy released? This food that you get, the food particles that you get, okay, the oxygen is required. The oxygen is required to break down these food particles. Respiration is nothing but what? The interaction of oxygen and the liberation of carbon dioxide. All right, so energy is released. Thereby respiration is also a exothermic reaction. And then talking about endothermic reaction. Endothermic reaction is nothing but chemical reaction where the reactants absorb heat energy from the surroundings. The reactants absorb the heat energy from the surroundings to give rise to products. Okay, these reactions lower the temperature of their surroundings, thereby creating a cooling effect. That is, they require energy for the process to actually take place. So they are taking energy from the surroundings. Thereby they are taking energy from the surroundings, making the surroundings cool. All right, and let me tell you, decomposition reactions are nothing but, all of them are nothing but endothermic reactions because they require energy either in the form of heat, electricity or sunlight. And when energy is utilized, when energy is taken up for the reaction to take place, such reactions are known as endothermic reactions. So now talking about combination reactions, these are some of the examples of combination reaction, that is where two reactants, carbon and oxygen, are reacting to give rise to a single product, carbon dioxide. Where two reactants, hydrogen and oxygen, are interacting to give rise to a single product, water molecule. Alright, so these are all the examples of combination reaction. Now let's understand decomposition reaction, and decomposition reaction is nothing but, if I have to say, reverse of, it is the reverse of combination reaction. It is the reverse of combination reaction because a single compound is going to break down to give rise to two or more products. A single compound, a single reactant is going to break down to give rise to two or more products. And what was combination reaction? When two or more reactants interact to give rise to a single product. Is it not the reverse? It is the exact reverse of combination reactions. So decomposition reactions, I can also say, are nothing but reverse of combination reactions, and they are of three types. Thermolysis. Lysis means breakdown. That is, here breaking of bond is going to take place. Breakdown is going to happen. Thermolysis. Electrolysis. Thermolysis, that is, you're going to use heat in order to break the bond. That is, heat is going to be absorbed. That is the form of energy. In electrolysis, we are going to use electricity. And for photolysis, we are going to use sunlight. So breakage of bond is going to take place by the absorption of energy, and this energy is either provided in the form of heat or electricity or sunlight. So this is about decomposition reaction in a gist. Let's now see the examples. So in thermal decompositions, we know it is caused by usage of heat. At high temperature, the reactants absorbs a lot of energy and it breaks down to give rise to two or more products. What are the examples for this? The best example for this is iron sulfate. Iron sulfate, the green color iron sulfate. Okay, the green color iron sulfate, upon giving heat to it, it gives rise to a brown color, reddish brown color ferric oxide. Okay, reddish brown color ferrous oxide, ferric oxide, reddish brown color ferric oxide with sulfur dioxide and sulfur trioxide gas. Ferric oxide with sulfur dioxide and sulfur trioxide gas. So when you're heating this ferrous sulfate, this green color ferrous sulfate, in a test tube, it liberates gases, that is sulfur dioxide and sulfur trioxide. And this ferrous sulfate, which was green in color, turns to reddish brown ferric oxide. Reddish brown ferric oxide. Some other examples are when calcium carbonate is subjected to heat, we get calcium oxide and carbon dioxide. Now, don't you see a single reactant is giving rise to multiple products? Similarly, with lead nitrate, a very important example, a very important example, because this nitrogen dioxide which you see is a brown color gas. It is a brown color gas. So they might ask you that, okay, when the lead nitrate is heated, a brown color gas is released. Where is this brown color gas coming from? Nitrogen dioxide. And this lead nitrate, upon heating, gives rise to three products, which is lead oxide, nitrogen dioxide and oxygen. So are these not decomposition reactions? They are. A single reactant is giving rise to two or more products in the presence of heat, thereby thermal decomposition. Let's now look at electric decomposition. Clearly, the energy is provided through electricity. It is provided through electricity, thereby it is also known as electrical decomposition or electrolysis, since lysis means breakdown. Alright, beta? Lysis means breakdown. So, water, when electrolyzed, that is when electricity is passed through water, what we get is hydrogen gas and oxygen gas. So when electricity is passed through this water molecule, what we get is hydrogen gas and oxygen gas. And you must see that it is balanced. But you need to make sure of one thing. That is, Whether or not they ask you to balance a reaction, if you're writing a reaction, it is your duty, it is your responsibility to balance it, because the law of conservation of mass must stand true. All right. So if you're mentioning a reaction, when you're, let's say there is a question asked regarding decomposition reaction, you're going to explain all the three types, thermal, electrolytic, and then obviously photolytic, right? Now when you're putting forth this along with explanation, you will also write down the equation. You have to, just like how you have to write down a formula in physics when you're explaining a concept or a theory, similarly you have to write down the reactions if you're explaining any of them. And when you're writing down a reaction, it is your responsibility that you balance it. If not, they are going to cut your marks. All right. So don't do that to yourself. When mentioning a reaction, do mention a reaction, and when mentioning it, make sure it is balanced. So water interacting in the presence of electricity will give rise to, when it breaks down, it gives rise to hydrogen gas and oxygen gas. So water molecules, its interaction is there. When you provide electricity to it, it breaks, and what we get is hydrogen and oxygen gas. So this is electric decomposition, very simple, to the point. And finally, photo decomposition. Photo means light. And with light, what we talk about over here is sunlight. Okay, sunlight. When you're exposing a compound to light and it is capable to undergo decomposition, it is known as photo decomposition. And AgCl, that is silver chloride and silver bromide, are capable to undergo. They're capable to undergo photo decomposition and give rise to silver and their respective gases, which is chlorine and bromine. But this is used, they have this application, photo decomposition have an application in black and white photography. So it has its application as well. This is something that you need to remember and do mention when you're explaining about photo decomposition. So with this, we have understood combination reaction, decomposition reaction, and its various types. Let's now talk about displacement reaction. With the term displacement, you understand something is being displaced. Now when you look at this, A plus BC is giving rise to AC plus B. Okay. Now what do you see over here? Is this A not displacing B and interacting with C and giving rise to just B in the end? Is it not displacing C? Let's say there is me. Okay. And I have this pen, this presenter in my hand. Now, if a very, a very thin person, and here I'm talking with respect to their weight only, okay? With respect to weight, it has got nothing to do with strength. I'm just relating weight with strength. Let's say a very thin person comes and is trying to snatch this presenter out of my hand. Will not be able to. Why? Very thin, no, he will not be able to. But if there is a sumo wrestler who walks in and tries to snatch this from me, I will happily give it off to him. You know what? Take it, bhaiya. I don't want it. So what do you understand over here? The sumo wrestler is bulky. It has a lot of strength. Whereas the thin person does not. So this A is being able to replace B, displace B. It is able to snatch C away from B. What does this indicate? A is stronger than B. But in what sense? In its reactivity, in its ability to react. Okay, so displacement reaction takes place only when A is more reactive than B, when it reacts more strongly than B, that is more reactive than B. Had A been less reactive than B, no effect. The displacement would not have happened. But since A is more reactive, it can very happily displace B and interact with C and leave B alone. But what is this reactivity? Where is the term reactivity coming from? So reactivity is nothing but a measure of how readily a substance undergoes a chemical reaction. How readily a substance is willing to react. How happily, how nicely a substance, how readily, how fast is its reaction. How ready it is to undergo a reaction. That is what is reactivity. So ma'am, how do we determine which is more reactive, which is less reactive? Very nice question. Is there an order? Nice question. Yes, there is an order. Okay. And this is nothing but the reactivity series. We understand that with the help of reactivity series. The elements that are present on the top are more reactive than the elements that are present below them. That is why the elements that are present on the top can displace the elements that are present below them. Got it? I'll repeat again. So elements that are present on the top of the reactivity series are more reactive and can very happily displace the elements that are present below them. But the elements that are present below in the reactivity series cannot displace the elements that are present above them, since the reactivity is less. Whereas the elements that are present on the top, okay, they have a higher reactivity. So this is about the reactivity series. And how do you remember them? Potassium, sodium, calcium, magnesium, aluminum. Instead of actually trying to remember them where you might get confused, there's a very simple mnemonic, which is, please stop calling me a careless zebra. Instead, try learning how copper saves gold, where the very first letter is telling us about the element. The P in please stands for potassium. The S in stop stands for sodium. The CA in calling stands for calcium. The M in me stands for magnesium. The A stands for aluminium, so on and so forth. So this is the reactivity series. Let's now see a certain few examples. Zinc, when it reacts with HCl, hydrogen lies below zinc in the reactivity series. So zinc very nicely, displaces it and forms a salt, that is zinc chloride, along with liberation of hydrogen gas. Alright, when zinc reacts with copper sulfate, again, copper lies below zinc in the reactivity series. So zinc very happily, displaces copper, and what we get is zinc sulfate and copper in its solid state. So this is about displacement reaction. Now talking about double displacement reaction. Oh, that is, the displacement is taking twice double. How? Two of the elements will be displaced. Now look at this. AB plus CD gives rise to AC plus BD. That is, this A is displacing D and is interacting with C, and this B is displacing C and is interacting with D. The example that you can see is barium chloride interacting with sodium sulfate to give rise to barium sulfate, which is a precipitate, and precipitate can also be indicated with a downward arrow along with the formation of sodium chloride. Another example that you can see is when base reacts with acid, NaOH is reacting with HCl, we are getting NaCl and water. So what do you understand over here? In double displacement reaction, precipitates are formed. Okay, not necessarily that always a precipitate is formed, but there is a tendency of precipitate to form. Also, look at the states. All of them are in the aqueous state. That is, the reactants are in the aqueous state. When I say all of them, I mean the reactants. The reactants that are there, they are in the aqueous state. When reactants are there in the aqueous state, it is easier for them to displace each other. Alright? So the reactants in both the cases are in the aqueous state. That is, the displacement takes place when the reactants are in the aqueous state. Only in the aqueous state can the displacement take place. Had they been in the solid state, the displacement wouldn't have taken place. Alright? So this is what you notice. That's the first thing you notice. Next thing that you notice is that precipitate is formed, and that can be shown by a downward arrow as well. And another thing that you have to notice is neutralization reaction is an example of double displacement reaction. So with this, we have covered double displacement as well. Now talking about redox reaction. Redox reaction is the short form of reduction oxidation reaction. That is, both reduction and oxidation are going to take place simultaneously. Thereby, we classify them into one class, which is nothing but redox reaction. Alright, and when reduction and oxidation take place simultaneously, they go hand in hand. Such reactions are known as redox reaction. And all the redox reactions can be broken down into two different processes, which is nothing but reduction and oxidation. The oxidation and reduction reactions always occur simultaneously in oxidation reduction reactions. All right. Now look at this. Heat a china dish containing about 1 gram of copper powder. What do you observe? So when you take copper and you're heating it in air, that is, oxygen is being added to it. What do you get? You get copper oxide. All right, you get copper oxide. Now, what do you see over there? Oxygen is being added. Oxygen is being added. So oxidation reactions are those reactions in which oxygen is added during a reaction. Then the reaction is said to be oxidation reaction, and that substance is said to be oxidized. That substance is said to be oxidized. All right. So this is about oxidation reaction. You can also say, along with gaining of oxygen, you can also say when hydrogen is eliminated. Okay, when hydrogen is eliminated, I'll write it as hydrogen instead of H2. When hydrogen is eliminated or removed, even then it is known as oxidation. So this is about oxidation reaction. Now talking about reduction reaction. Now what does it say over here? What would happen if hydrogen gas is passed through CuO? So when I take CuO and over this I am passing hydrogen gas, I get copper plus H2O. Plus H2O. Now what is happening over here? The oxygen is being removed from copper and it is being added to hydrogen. So what do you observe? Such reactions are known as reduction reaction. That is, substance loses oxygen during a reaction. It is said to be reduced. I can also say when hydrogen is added, it is said to be reduction. Also, you either have to take one, that is, either you have to say oxygen when it is being removed or when hydrogen is being added. Okay, either of the two, not both of them. All right, either of the two. All right. So what do you understand over here in redox reaction? During this reaction, the copper oxide is losing oxygen and is being reduced, whereas the hydrogen is gaining oxygen and is being oxidized. In other words, one reactant gets oxidized while the other gets reduced. Such reactions are known as oxidation reduction reactions. In simpler terms, redox reaction. Now there is another term that I want to introduce to you, that is oxidizing agent and reducing agent. Now there is one thing that I want to clarify. Okay, let's say you want chocolates. Let's say you want 2 chocolates and I have 10 chocolates. You come and you ask me for chocolates. You're like, ma'am, you have 10 chocolates. Can you give me 2? Since I have 10, I can give you 2. But let's say the thing is reversed. I have 2 chocolates and you want 10 chocolates. Now you come to me and you're like, ma'am, I want, you want 10 chocolates, right? You come to me like, ma'am, I want 10 chocolates. How can I give you 10? I only have 2. Now, understanding this logic and applying it over here, oxidizing agent, that is, it is going to oxidize others. Oxidizing agent, it is going to oxidize others. It is an agent. It is going to oxidize others. It can oxidize others only if it has oxygen, right? Only then can it donate oxygen. But when you look at this, when an element is trying to oxidize, when a substance is trying to oxidize others by giving away its oxygen, is it not getting reduced? That is, when you come and ask me for 2 chocolates out of 10, I am giving you 2 chocolates, but that is reducing the number of chocolates I have, right? Right. So what do you understand over here? Oxidizing agents are those, okay, oxidizing agent, I'm writing it as OA, are those which oxidize others by itself undergoing reduction. Reducing agent, on the other hand, opposite of this. Okay, so reducing agent is the one that will reduce others by itself undergoing oxidation. And where do you check for this oxidizing and reducing agent? Always in the reactant side, never on the product side. Always on the reactant side. So, the element or the substance that is undergoing reduction becomes your oxidizing agent, and the one which is undergoing oxidation becomes your reducing agent. So this example that we took over here, that is when copper oxide is reacting with hydrogen, is giving rise to copper plus water. Now we know copper oxide is undergoing reduction. Since it is undergoing reduction, it is an oxidizing agent. Okay. Whereas this hydrogen, it is undergoing oxidation by gaining of oxygen. It is a reducing agent. Clear, beta? So with this, we have understood about oxidation and reduction reactions, and we have also understood about oxidizing agent and reducing agent. Let's now try to see the effect of oxidation and reduction in our everyday lives. Corrosion. What do you understand by the term corrosion? Corrosion means to destroy, break down, to tarnish. That is what you understand by the term corrosion. So what happens is, you must have observed that the color of the coating formed on copper and silver when you leave it in air, okay, or the iron that you see, after a while it gets a reddish color on it. Okay, what is this? Corrosion. Okay, what is this? Corrosion. Here it is reddish brown because of corrosion, and here it is silvery, shiny silvery. Okay, so what do you see? The stark difference is because of corrosion. Now for iron, it is known as rusting. Rusting is a class of corrosion, but for iron. It is for specific element iron. But corrosion is also seen as the black coating on silver and green coating on copper. Okay, so corrosion causes damage. It causes a lot of damage, beta, because see, metals are now a part of our living. They are. The buildings that you see, their foundations have metal rods in them. The huge pulls that you see, the huge bridges that you see, they have iron in them. The pulleys, iron. So you see metal everywhere, and predominantly iron. The automobile that you use. Now you tell me, these huge bridges, it is made up of iron, right? Now since it is made up of iron and it is exposed to air, will it not undergo corrosion? It will. Will it not be fatal if it breaks? Because what happens is, let's say this is a piece of iron. Okay, it undergoes corrosion on the surface, and corrosion, by the way, is a surface phenomena. It is a surface phenomena. Okay, now upon corrosion, what happens is, this layer, okay, is lost as iron oxide and it becomes thin. Don't you see that the diameter, it has become thinner? So don't you think it is going to affect the strength of the iron? And imagine those huge bridges in the foundation which you have, those rods. What will happen if they get corroded? It can cause a lot of damage, so much so that it can be fatal to the life. So how do we protect it? We can protect it by coating the surface, by painting it, greasing it. Alright, when you cover the surface, see, it is a surface phenomena. All you have to do is cover the surface. When you cover the surface, then the surface is no more visible, no more viable. Okay, it does not come in contact with the oxygen, with the humidity, thereby being protected from undergoing corrosion. So this is about corrosion, and this you can see how it affects badly to the bridges and the various other examples. All right. Another form is rancidity. Rancid is, the fats and the oils that you have in your food, they get oxidized. And because of this, they taste different, they smell different, and they are no more good for consumption. All right. So that is rancidity. So what do is, we add antioxidants in them, we add preservatives in them to prevent them from undergoing oxidation. We also add nitrogen gas, the chips that you eat. You see that, they are in puffed packets. Where is that puffiness coming from? They put in, they insert nitrogen gas, because nitrogen is a less reactive gas. Okay. So they insert nitrogen so that it does not come in contact with oxygen. So this is how oxidation and reduction has its effect on our day-to-day lives and our everyday lives. So with this, we have understood the entire chapter, which is chemical reactions and equations. We have summarized all of it. And what all have we learnt? We have learnt about the various properties, okay, of a chemical reaction, properties of a chemical reaction, okay. Then we learnt about, apart from this, we learnt about balancing of equations, okay. And this balancing of equations is done because we follow law of conservation of mass. All right. Then we have learnt about the different types of reactions, and we have 5 major types of them. So this is what we have learnt. We have learnt about exothermic reaction, endothermic reaction, reactivity series, reducing agent, oxidizing agent. We have summarized the whole of it and the entire process and all the different conditions, everything that is there when a reaction is taking place with all the different chemical reactions. So with this, we have finished our summary. Let's now do a certain few questions that have been asked in the boards. So this question came in the board exams 2020, which is assertion and reasoning, which is, following is a balanced chemical equation for the action of steam on ion. The reason is the law of conservation of mass holds good for a chemical equation. So now we have 4 options, both A and R, that is both assertion and reasoning are true, and R is the correct explanation of A. That is the first option. Second is both A and R are true, and reason R is not the correct explanation of A. Okay. Then option C is A is true but R is false. And option D is A is false but R is true. So we know that yes, this is a balanced equation, and we know that yes, law of conservation of mass holds good for a chemical equation. Thereby, option C and option D are discarded. Now it is between option A and option B. Now how do you understand? Now how do you reach out, or I would rather say think or tackle questions like this? Simple. When assertion and reasoning is asked, you have to read it like this. Balanced chemical equation is good because law of conservation of mass holds good for a chemical equation. Just add the term because after reading assertion and before reading reason. And after adding the term because, if it makes sense, then option A is the right answer. If not, then option B is the right answer. In this case, option A is the right answer, because balanced chemical equation for the action of steam of ion is good because the law of conservation of mass holds good for a chemical equation. Yes, it makes sense. Thereby, option A is the answer. Let's now look at another question which came in 2020. When hydrogen sulfide gas is passed through a blue solution of copper sulfate, a black precipitate of copper sulfide is obtained and the sulfuric acid so formed remains in the solution. The reaction is an example for. Now for this, they have given you an entire sentence of a chemical reaction. First, you write the word equation. Then you write the chemical equation. So we will write the chemical equation and we will check, okay, CuSO4 plus H2S gives rise to CuS plus H2SO4. Then you balance it. Now, isn't there double displacement taking place? Copper is interacting with sulfide, sulfur is interacting with hydrogen. Therefore, it is an example of double displacement reaction. Let's now look at the third question, which came in 2013, which is state the law that is followed by balancing a chemical equation. Now this you know is law of conservation of mass, where you say that law of conservation of mass is followed and you explain law of conservation of mass. Then balance the following chemical equation. So we will balance the equation as well. So first you will write about law of conservation of mass, okay? Okay, and then you will balance the equation, and upon balancing, this is what we get. That is 2Na plus 2H2 will give rise to 2NaOH plus H2. So with this, we have summarized our session. We have summarized the first chapter along with doing a certain few questions. So I would now like to thank you all for being a part of this session. Okay, I thank you all for being a part of this session, and until we meet next time, keep studying, keep learning, and stay healthy. Until then, bye-bye.